optimistic about the fame of this department, and this department is doing very excellent job. And I understand that the department will continue this specialization for in the next 1 year. And I, on the behalf of the university authority, I wish any success of this celebration. Thank you for inviting me.
We'd like to felicitate the registrar with the bouquet of flower and a memento, and that will be given by Professor Meghnad Das. Now, I would like to request Professor Basu if that book that can be launched by the researcher.
Oh, yes. Honor. আরে নিজেদের টাকায় আমি
Wonderful teachers. Our wonderful teachers, by written, compiled, and edited by Subhash Chandra Dutta Ray, Prashanta Kumar Basu, and Chinmoy Kumar Maiti. Chinmoy Haji? আচ্ছা ঠিক আছে এর মধ্যে আরো অনেক আছে এক্স স্টুডেন্ট ইত্যাদি ইত্যাদি তাদের মানে রেমিনিসেন্স এন্ড মেমোয়ার্স আছে এবং প্রচুর গল্প
I just apologize one thing that we are not able to deal this slide because the whole program has been streamed live in YouTube and they need some light so that it can be seen by from the other end. So that is why we cannot deal this slide. So please forgive us. So our next speaker is Dr. Amit Kumar Patra. Is director of NARL, National Atmospheric Research Laboratory. And first of all, I request him to felicitate with a bouquet of flowers. Sir, please. So I introduced Dr. Patra before you, and at the same time, we can prepare the slides. I think you want to show the slides, so that's in here. So I need your request. So Dr. Amit Kumar Patra is currently the director, National Atmospheric Research Laboratory, and his research interests includes atmospheric and ionospheric physics, ionospheric electrodynamics, and plasma irregularities, space weather, radar probing techniques. He got a lot of recognitions and awards from INSA, Indian National Academy of Sciences, PRL Award, and member of several important committees like ISRO, RC, and AIS, and expert committee member of ACRB and many others. He has supervised more than 8 PhDs, and he has edited more than 135 publications in peer-reviewed journals. So with this, I request Dr. Patra to begin his talk.
Very good morning to all of you. At the outset, I would like to thank the Institute of Radio Physics and Electronics and the University of Calcutta for inviting me for this particular occasion. I'm extremely happy to be here on this particularly to commemorate 75 years of excellence. I think this particular institute was born when we were not born, and we do radio science, we came here. And so I'm extremely happy to be here today, and I'm able to see many, many teachers. They have not taught me, but they are able to teachers, and I have learned many, many things about this particular institute. This is a great relation for me, learning about this. Today we are here to celebrate the 75 years, and radio science is a very vast subject, and indeed it is not possible for me to cover all the domains that currently we are pursuing. But I will, with my background, I will take you to the radar probing of atmosphere and atmosphere. And I have taken this particular subject. The reason is that many of you know that in the current radar field station, with 53 megahertz high power radar is coming up. It is about to be implemented. It is almost in the final stage. I'm extremely happy also to tell that towards the end I also served in the project committee, implementation committee. So I have some opportunity to learn something about the background and so I will not really venture into radio science in broad sense, but I will also start that where from the radar came into the picture that we use today for atmosphere and atmospheric probing the soft target. So radars are there for the hard target for military applications. So a little bit of background. But so what I am going to do is that I am going to have a brief historical background of radio atmospheric atmospheric science from where we took off. This talk is made using the first generation high power large aperture radars that came with some hypotheses, and then recent advances in radar probing that we are pursuing today, and particularly the University of Calcutta radar system, as I understand in the future prospects. So this is how I will go. So if we go back in time without going into detailed story, how the ionosphere came into the being, and you know this is around 1901 that Marconi's experiment you all read in the book, that he did the first transatlantic radio communication, and it proved that the radio wave can go beyond the horizon. That's the basic concern without knowing what actually inflated the radio wave. But there was some kind of inference that something must be there in the atmosphere which is conducting, which is reflecting the radio wave coming back. That's how it came. But the atmosphere truly was not discovered. So it is 1924, I think we know all the story, that it is Appleton who actually conducted the experiment and then truly first time recognized that there is something called atmosphere. And of course, he continued the work on atmosphere, and we know that in 1947 he was given the Nobel Prize in Physics. But truly, if you go into the history, then you see that in 1926 a power radar was developed by Britt and Tugay in the United States, and that was the first, I think, first radar.
Was it marketable or JC course?
No, this is JC posting was millimeter wave, which was line of sight communication, which was not over the horizon. So, because millimeter wave cannot propagate over the horizon, it is only the high frequency which will propagate because of the reflection of the atmosphere. So the Britain today, this truly the radar. If you want to go back, I think this is the first thing that we should recognize that a radio pulse was sent and the ranging was done. So radar stands for radio ranging. So that's how it came. But then we have come beyond that. Now this is the international scenario. Now if you come to the Indian context, we all know that we were here. I think it is around 1930. I think the experiment which Professor Mitra conducted from Meghnad. This is how that E region and D region signals were actually received. The very region I understand that he was using actually the radio frequency waves. So these waves actually cannot penetrate deep into the atmosphere because of the frequency. So they get reflected from the D region and E region depending on the density. And I think today morning I heard that D region was the one which was actually truly discovered from Bhutan. And E region was more of a what is called confirmation of what Appleton and others did. But what is important is that this particular institute where we are sitting today, it was actually established in 1949. There was also something I said about it, and we are completing 75 years. I think it has a very illustrious history. And I think this 1955 I read from some literature, but today morning I learned that it is 1950. So there could be somewhere. So the Haringhata field station came in, particularly the ionospheric field station, from where the radio, the ionosphere kind of experiment was conducted worldwide and become part of the worldwide chain. So that's how I think we have a very great heritage, very rich history about radio science and ionosphere together, and of course the atmospheric skills came later, and which I think I read in the book and also in the literature. There is something called Celia. Truly, whether it was Celia or not, that is something that had to be really debated. But the frequency that he was using, it was medium frequency. So that is one thing that was I have some doubt about it. So this is the kind of system, the background that I was talking about, whether it is Appleton, whether it is Great Tube, this is the Professor Mitra. I think all these they were using mostly medium frequency, high frequency, because everything started from the communication those days. And then the radar thing actually got the boom from the World War. So that's how most of the radars were developed for the defense and the military purposes. But later on, they were improvised, and then today the radars are very, very sophisticated. I will come to that later. So this is what we call as the typical ionosphere. This is the sweep frequency, high frequency actually is one, and you can transmit up, and depending upon the plasma frequency, you get the signal back. So you'll be able to derive the electron density up to the peak of the layer. And this is the very powerful workhorse. Many years people have been using it, and now also people are using it because it's very, very cheap today, and very, very useful for the background diagnostics. So this is actually the modern era started of the radar. In 1958, Bill Gordon, he actually calculated that it is possible to actually detect an individual electron which comes from the Thomson's category if you have very high power radar. Aperture something of the order of 300 meter diameter, this or 300 meter square or whatever it is, kind of an antenna, and a couple of megawatt power. So if you have this, it is possible to actually detect individual electron coming from the Thomson's category. That's the theory that he proposed, and he showed the calculation that if you have an antenna at the order of this size, it is possible. That's why if you look at the early radars, these are the two radars which came up, one at Erisubo, at Puerto Rico, and now this has been dismantled. But this was actually used not only for the ionospheric research, but also for planetary science and astronomy. And the very reason is that Gordon himself was fascinated with astronomy, so most probably that took that turn. But the other one, which is a 50 megahertz radar located at Peru, Lima, Peru, and this is a 300 meter by 300 meter square array, 10,000 number of antennas. They are not Yagis, they are basically the Cocos. And so that's established right over the magnetic equator, both systems actually came around the same time. And we all know that all that we know from the atmosphere, much of it actually came from Vikramarka. And all that the discovery that we know in the astronomy, that came from the Arecibo. Not all astronomy, but this particular radar which was built for atmospheric research with the motivation that the Thomson scattering can be detected by high power radar, actually was not used in that sense completely, but it was used for astronomy. And a lot of discoveries that have a Nobel Prize have been provided, given and things like that. So that's the early story after Bill Gordon wrote that. So this is what is the background about really the first generation high power radar. The first one being at 430 megahertz, and second one is 50 megahertz. So it has an advantage that when you have the radar frequency very high, you can really actually penetrate deep into the device shielding area, and you'll be able to really address the electron. So you will get the scattering, which will be almost like Thomson scattering. But when you talk about 50 megahertz, actually the device shielding that area, the diameter is much smaller than the radar wavelength. So the radar wavelength does not penetrate deep into the device shielding area. So what you get is more like the fluctuations in electron density kind of thermal fluctuation, and you don't really address the electron as an individualized thing, but it's more like a collective thing. So you don't get really the Thomson scattering, but you get something kind of fluctuations from electron density, kind of back scattering can be used. That's how actually many things, the products that we got from the Arecibo 430 and the Vikramarka 50 is very different. So you could go to the top side of the ionosphere using Vikramarka, this kind of device shielding and the long radius, all these limitations will not come into the picture, but once you go into 430, you will see that you will have the upper ceiling, you cannot go beyond the point. So that's why you never did any observation on the top side, it's only the Vikramarka. So I will quickly just try to cover that what kind of breakthrough has happened. It is around 1964, 65, 66 time frame. I think most of the theory, most of the observations came through. But the major breakthrough happened, what we call as the two-spin plasma instability, when the electrons and ions are moving with differential motion, and the differential motion exceeds the ion thermal speed, kind of 330, 360 depending on the temperature, then the plasma becomes unstable. So you have the plasma waves. And those plasma waves will be moving with the ion density speed, something of the order of 330 to 360 meters per second. That's the first verification. And the theory was already established by Don Carly, and it was confirmed by the Vikramarka observations. And then soon after that, I think several experiments were started even from India, for example, Kumba or Prakash, they were all confirmed. So this is one very important discovery for plasma waves. There is another kind of wave when the electrons do not move with respect to the ions with that speed. That means the electric field that is there, that is not sufficient to drive the electrons at such a high speed, but that means the electric field is very low. But you have the density gradient, so the density gradient of the electron grid together can make the plasma unstable, what we call as a gradient instability. But what happens is the gradient instability occurs at a much larger wavelength to start with. It cannot happen actually at a small scale because they are dissipated. So by diffusion. So this is a kind of observation that came, for example, you take the 50 megahertz radar, so the wavelength is 6 meters, so the back scale will be of the half lambda, so that is 3 meters. So at 3 meters, you imagine the 3 meters, so the waves cannot grow because they are basically damp waves. So there are a lot of actually speculation those days how to explain the radar observations. I'll come to that later how this kind of thing happens. But this is one of the major breakthroughs. Why this is a breakthrough? Because once you think about the E region, you have the electron density going up with height, and the electron density going down, and then you have the F region. So you have the positive gradient, and you know for sure that the electric field in daytime is upward. So with upward gradient and upward electric field will make the region unstable. So the top side is going to be stable, and all these echoes were actually confined practically to the lower part of the region. That's how the theory came in. The gradient instability was confirmed later using rocket observation. But when this puzzle, why 3-meter waves are growing, they are not supposed to grow as far as the theory is concerned. So this is where the two-step process or the mode coupling came into the picture. This mode coupling is more like turbulence. Two-step is more like linear. So what happens when you have the e-vision, you have the electrons moving in the zonal direction because of the vertical upward electric field. So you have the plasma waves actually growing in the zonal direction. So plasma waves means the high density, low density, high density, low density regions. When you have enough density gradients, they will break secondary irregularities in the particular direction. So this is the cartoon. You can see that there are high density, low density regions, and you have the gradient. So you will have the plasma waves moving up and down. This is what radar will see. Because the basic gradient is very stark because of the scales. So you will have the next level, the cascade in the just like cascade of energy, you will have the smaller scale over there. So this is a two-step process. This is actually the mode coupling. So if you have plasma waves in different directions, so two waves when they couple, then you will have the third wave generated. You can see varieties of waves like the K1, K2 will give you the K3 in different directions. So in a way, the plasma has become nonlinear, so it becomes turbulent. So if you look at by radar in all directions, you will be able to see back scattering coming from all directions. More like isotropic around the magnetic field, not around the magnetic field. Along the magnetic field, highly anisotropic. So that's how the thing happens. You see, this is all theory, but actually the true confirmation of the two-step process, where you have the primary waves generated in the east-west direction, which gives you the secondary waves, either through the two-step process or through the mode coupling. You can see this is something that has come from the radar interferometry imaging. This is a borrowed concept from the astronomy, because astronomers use multiple receivers in space and try to actually resolve the sky. So this is the same concept. So you receive the signal from the same source or multiple sources by different receivers separated in space. The kind of resolution you want, you do the separation like this. So the radar interferometry is done in the same way. You send the radio into the sky and receive the field at different locations and do the cross correlation between the receivers. And if you have more number of receivers, you can do true imaging. And that's a very beautiful thing to learn about the very small scale processes, the hotspots that are growing, how they are growing, how the fading is happening in the turbulent scales. So this is something that came in. So this is a very modern technique which people adopted, and most of the radars today, as we will see in Calcutta radar, it is also equipped with multiple receivers to really facilitate the researcher to do very high class research, not only to do the plasma, but also to read the atmosphere, the meteor, the meteorites, many things. So this is another invention which came actually as a major breakthrough. The F region became unstable. In the iron ocean, they were seen as a spreader because so nobody knew that what is the source. So finally it turned out that this is the plasma. So this is the background plasma, the incoherent scatter output, and then you see after the sunset, actually the plasma becomes irregular. So the top, the bottom, and top, everything is unstable. So it was very difficult for the theorists to actually digest that how the top side is going to become unstable. Because even if you think a relative stability is taking shape, which was already in the world, so they thought that it's only the bottom side which will be unstable, the top side is going to be stable. But when this relative, the low density plasma is moving through the high density plasma, it is getting polarized, it is becoming nonlinear, it is going to the top side in the way it is making the plasma unstable. That's how the theory came in. So it's a great contribution by radar to link the theory and the observations. So this is a very classical example that you are seeing the plumes, they are called radar plumes. The plumes are nothing but the radar backscatter, whatever you get from the ionosphere, you plot it as a function of height and time, so you get the plumes. So these plumes are actually represented in the problem. But you'll be surprised to know that when this was done somewhere around 1975-76 time frame, till today, nobody even today was able to relate that indeed these plumes are linked with depleted plasma regions. This is something, the plasma bubble, whatever we call. So they are linked indeed with those that was not established. I will show you that it has been done only recently. So it is again become marker because a very high power system, 300 meter by 300 meter antenna with about 8 megawatt peak power, and so it was made for atmospheric research, but very soon they realized that the background ionosphere cannot be studied over the Kamaka because you are right over the equator, you have all the large electric fields, and these electric fields and current will not allow the plasma to be present. Plasma will always become unstable or something or other. So most of the time, instead of doing the incoherent scatter work to study the background ionosphere, they actually got trapped into the plasma irregularity. So that's why all these enhancers, whatever that happen from the Kamaka, they are more of plasma irregularity, plasma waves, plasma turbulence. Then they have a linkage to what today we call the ionospheric scintillation, the satellite signal coming from the ionosphere, which include varieties of scintillation, including L-band. L-band is very important because L-band they are using for navigation. So it is very, very important that this scintillation needs to be studied, this forecasting has to be done properly, otherwise there will be errors. The errors at one time possibly was okay, it was acceptable, but in today's demand, I think the precision that people want, that the accuracy people want in positioning, I think this needs to be fully characterized and then predicted properly. So this is where we stand today. So this is another major discovery and breakthrough in the high power radar project. In 1974, a seminal work was published by Ronald Mann. He was the director of the Kamaka Radio Observatory, and what he found, what is shown there on the x-axis is the height that we use in the radar pulse, and you get the return from every height, which certain height resolution. So you go up to almost about 90 kilometers, and then what he was doing is that you are just adding pulse by pulse, and just adding. So he's just plotting the power here on the y-axis, and x-axis is the time. And you see that the lower height up to about 30 kilometers, the power is quite good, and from 30 kilometers to 50 kilometers, the return power is less, and that power is more like noise. And then again there is so this is where because this is not the usual practice in incoherent scatter radar, because the electron lifetime is very, very short. So you cannot do pulse by pulse integration. So you have to do the entire spectrum in one pulse itself. You have to send the pulse, get the signal to the spectrum. That's how the incoherent scatter works. But here, when you are sending pulse by pulse, the lifetime does not allow to do that. But in the troposphere, stratosphere, and mesosphere, where you do not have such kind of thing, you are basically targeting the refractive index fluctuations. So the lifetime is fairly good. So you'll be able to integrate. You'll be able to integrate. This is how this concept came from MST technique, mesosphere, stratosphere, troposphere. Basically, this radar was not made for that, but he ended up with this result saying that it is possible to detect signal from mesosphere, stratosphere, and troposphere. So this is how the MST radar technique came. And today, in most of the countries, whatever people are using for probing the atmosphere is not the weather radars, but the background ionosphere. So this is the technique, what is called as mesosphere, stratosphere, troposphere. It is not, it just came because signals were received from other regions. That's all. But the basic concept lies here. You send a pulse, get the return from all heights, send the next pulse, get from all the height, and you just add them. Keep on adding. Up to certain time, you believe that the correlation time will help us in building the signal because noise is random. So noise will get captured and signal will build up. So this is what we call the addition coherently. So if you add coherently, all pulses in coherently when you add, the signal builds up, noise gets captured, so you improve the signal to noise ratio, and you'll be able to see the signal. This is how this particular concept came, and this is what we are calling here the ST radar. But I will tell you, it is actually not a good thing to tell ST radar. The power, aperture, whatever capability, it should be either called ST radar or it should be called as a simple radar. because the radar can be used for many purposes. Why only should be confined to testing? So now what actually we want to know in radar probing basically, we want to measure amplitude, we want to measure phase and polarization of the status to characterize everything. But if you have large number of receivers or more number of frequencies separate, they're closely separated, we will be able to gather more information about the target. So amplitude will tell us about the reflectivity that we use. Phase will give you the position of the target, and the rate of change of phase will give you the rate of change of position. That means it will give you the velocity. So that you can do. But when we talk about the polarization, for example, you have something which is isotropic or something which is anisotropic. So the polarization is going to tell you whether the target is isotropic or anisotropic. So this will tell you about that particular target. So these are the things, these are the parameters that are of interest to the radar scientists to characterize that. So for example, when you take polarization, you will be able to tell, you will be able to study raindrop, anisotropy of turbulence. Because turbulence at all scale cannot be isotropic. Small scale can be isotropic, but once the size increases, then automatically try to take the step of anisotropy. Even the raindrop, as long as it is small, it is isotropic. But once it becomes bigger, it is not going to be isotropic. So these are some of the very important parameters. For example, you are talking about something, some precipitation things, which is water, in the water phase. It could be isotropic or anisotropic depending on the size. But if you go to higher altitude, above the melting layer, the ice will become, the water will become ice. Once they become ice, then there is no shape, there is no defined shape. So you will be able to characterize whether you are really monitoring ice or water. So these are some of the very important parameters that we will be able to study electron density and electron density fluctuation. But what is very important today that we need to really realize that radar is a transmitter, antenna, you have a receiver. You send the signal, get back the signal, and analyze the data. But today's radar is not like this. You have multiple transmitter, multiple receiver. By doing multiple receiver, you are able to see a particular target from different angles. So you'll be able to see at what phase you are actually measuring it. By seeing the different set phase, you'll be able to localize them in the angular domain in the space. From the angular domain, you will be able to see what is the distribution in space. And then you will be able to locate all the hotspots from where you are getting the signal. The entire space that you are seeing in the radar class volume is not filled with targets, because in the field volume you will have only certain hotspots. There will be occasion where the entire field itself will be filled by so many targets. So you will be able to differentiate what kind of target you are addressing, what kind of turbulence, what is the anisotropy or isotropy, things like that, and how this is going to affect the other processes. Because when the atmosphere becomes dynamic, then it could, and if you have enough humidity, you have enough water vapor, it could result into cloud, result into weather. So these are some of the things which are of importance to us. So when you have multiple receiver, you can do interferometry, you can have multiple receiver, you can do imaging, you will be able to see the finer scale processes going down very close to the diffusion scales. This is something that is very important for a physicist. If you have multiple receiver, for example, with multiple frequency, so you set the frequency, let us say at 50 megahertz, then you change the frequency from 50 to 50.25 megahertz, very close by frequency. So the corresponding wavelength is different. The phases, if the target is here, the phases that you receive at the ground is going to be different. So by seeing the phases, you will be able to see what is the thickness of each layer. You will be able to see. Whether the question is, all that we see, whether they are just because of random fluctuation in the refractive index, or they are the layers in refractive index, you will be able to distinguish that whether they are just random fluctuations or they are just thin layers. For example, you can have viscosity layers. So when the viscosity layers are there, they are like some thermal ducts like this. So from those ducts you can see the signal, which is very different from turbulence. But in a big field target, you never know what is happening inside. So if you want to interpret data proper way, you need to know about this thing. Otherwise, you will end up in saying that this is the turbulence. Actually, there is no turbulence. So highly stable, they're all thermal, thermal waves. So this is the basically the concept. It is a kind of an assumption and for mathematical, what is called convenience. So in the crystal, when we do the X-ray diffraction, we create the black scattering. But in our case, what is happening when you have the radar wave vector going up? So you have the fluctuations in random direction. So what you get is you actually get the Fourier component along the ray path. You are not addressing the other component, only along the ray path, whatever be the. So when you do the Fourier analysis of the diffractive index fluctuation field along the ray path, you will get a component which corresponds to the half the radar wavelength, and that is what is going to give you. So today, whatever we are going to talk about, that all this ST, MST or atmospheric radar. So now it is very difficult to differentiate what is a ST radar, what is the MST radar, or what is the equivalent scatter radar. As long as your power and aperture is sufficient to get scattering from the free electron, you can treat it as a equivalent scatter radar. It all depends upon how you are going to analyze it. So if you are going to use only the fluctuations, you can call it stratospheric tropospheric radar. If you detect mesospheric signal, you can call it mesospheric radar. If you see ionospheric background signal, then you can call it coherent scatter. So I think giving a particular name is not justified. Better to tell whatever radar. I think that's more useful. So this is a very common technique which is used in the radar. You have the antenna. You can phase them electronically. You can tilt the beam, unlike in a disk. This actually physically has to be oriented if you want to tilt. But in a phase array system, you can actually tilt the beam electronically by giving differential phase to the consecutive antennas. So if you, for example, you want to measure wind, so you need to tilt the beam in a given direction to get the radial velocity from there. You want to measure the other component of the beam, you tilt in that direction. At least if you have three non-coplanar beams, you'll be able to get three unknowns in that direction. The east-west wind, north-south wind, and the vertical wind. So you get the entire wind field. And then the wind is not coming like a light spectrum because it is all filled due to turbulence. So you'll be able to characterize the signal in terms of turbulence. You'll be able to measure turbulence parameters and many things. So these are the kind of signal you can see even with naked eye. You can see this is the Doppler shift. On the right and the middle is the zero Doppler. There's the carrier frequency subtracted, and on the right side you have the positive Doppler. You have the negative side, the negative Doppler. You can clearly see that how well you can detect the central frequency of the Doppler separate signal. And of course, you can utilize this mathematics, and you can get all the physical parameters from the spectrum. So up to about 22, 23, 24 kilometers. With naked eye, you can see the signal. But with the sophisticated signal processing technique that we have developed in the recent years, including the artificial intelligence and machine learning techniques, you'll be able to go even deeper, higher up in height. So by doing that, you'll be able to study. So tropopause, which is where the temperature is troposphere, where the temperature is decreasing up to about 15 kilometers, and then above that temperature is actually increasing. So you are seeing signal even beyond that. So where the atmosphere is supposed to be stable because temperature is increasing with height, but you see that you are getting the signal. The question is whether these signals are coming from the diffractive index fluctuations or they are coming from diffractive index layers. This is something that needs to be investigated in the modern techniques. So you can get UPW continuously. The beauty is that you can measure continuously. See, when we talk about turbulence, the turbulence can be at very short scale. Within the radar pulse volume, you can have few meters to about 100, 200 meters scale because the radar will occupy a space which will be of the order of 100 meters square. Yeah. So but then if you continuously monitor the velocity as a function of time, you will be able to really see the large scale turbulence that we often encounter in flight. That it's a turbulent atmosphere. So those are, I think, something of very relevance to aviation industry. So this is the actually the spectra is broad, and the breadth of the spectrum is a measure of turbulence. But you have an artifact coming from the system that you need to subtract. But once you do that, you can get all these parameters, the eddy diffusion coefficient or eddy diffusivity and things like that. So these are of relevance not only from aviation point of view, but also from the pollution dispersion point of view. Because pollution is created at the ground, if there is no turbulence, essentially the pollution is not going anywhere, it's not getting diffused. So that it is very important to estimate and to go into the pollution modeling, dispersion modeling, so that you know how much pollution can be actually diffused. So this is, you can study the ground relay processes, you can study the rain, because when you are operating 50 megahertz, you get signal from the refractive index fluctuations, you get also signal from the Rayleigh scattering from the hydrometeors. Bigger the hydrometeors, you have bigger power, and you can get the rain drop velocity. So you will be able to study a lot of things about the rain drop size distribution, and their velocity and things like that. So they are of a lot of importance today. Rain recognition, for example, those who are studying from here, it's of use because you know the size, you'll be able to really establish the theory that what is actually on scintillation. So you can study also the melting layer, and you can see the ice versus water kind of bodies in the precipitation. You can study more detail about the topography and the kind of the thermal ducts which I was telling, the viscosity layers, very thin viscosity layers. They are of the order of 30, 40 meters, which you cannot resolve by any pulse, because your pulse length could be of the order of 1 microsecond or half a microsecond. 1 microsecond means 150 meters, half a microsecond is 75 meters. Okay, so you see the scales which are much smaller than the radar pulse resolve. So you will be able to do it by using local frequencies, at least 3 to 4 frequencies, close by frequencies. Because your radar is having a bandwidth, it is possible to transmit other frequencies and receive other frequencies because it has bandwidth. So it can be done. So you can study mesosphere. My own understanding is that the Calcutta University radar has all the capability to study mesosphere, and I think they can do that. You can study this. Actually, there is a theoretical challenge when it comes to the mesosphere. As you go up, actually the viscosity is increasing with height. So it is supposed to kill all the small scales. So if it is going to kill all the small scale, and as the theory suggests, less than about 10 meters, you are not supposed to see anything. But the point is that with the 50 megahertz radar, the scale is about 3 meters, you are seeing strong signal. Why are you seeing signal at 3 meters when the theory does not say? Where is that? Where from the energy is coming to the 3 scale? How this energy cascade is happening? Something that we need to talk about. Whether we are really getting from the turbulence or we are getting from some other processes. Something big question. And then the energy does not come from that scale. Energy comes from the larger scale. So the energy is injected at a larger scale. Energy is transferred from the larger scale to the smaller scale. The energy cascade. This is how we talk about the inertial subrange and the viscous subrange. So those things can be studied. So I think Calcutta is known for, because it's tropical and the latitude is such that you have quite often the very strong sporadicity. That means the very high density area which cannot be produced by photoionization. And it has its own repercussions today, because if you have plasma blobs or layer and the GPS signal which are used for example, the RO technique, the radio occultation technique for deriving atmospheric parameter, so they will be defocused. So there will be error in that. So all these GPS RO products, whatever you are getting in the wave, they need to be really examined, and you have a strong sporadicity. What kind of contaminations are happening? Because they are going into the model. So these are the very, very important and relevant thing as far as Kolkata is concerned. So there are beautiful things that are happening with what you call the toxic periodic echoes. Nobody knows today these toxic periodic echoes are due to the plasma law or due to the Kelvin thermal instability. If you have a shear flow, that shear flow can become unstable, and it can give you turbulence. So you see there is a beautiful picture. This is coming from the E region, and this is the FMCW data, which you see the weather data, and you see almost similar picture. This is nothing but pH, Kelvin thermal stability. And this is coming from the e-reserve linked in the fossil periodic glucose. So I think this is where the physicists can examine and differentiate between when it is going to lead to the plasma block becoming unstable and when it is going to be unstable through the pH sense. And so this is something that we can work. This is something very, very puzzling, which was discovered about 50, 60 years ago. But even today, nobody knows what is the physics that is driving this plasma entities. As on today, we know there are a lot of fine structure. On the x-axis you have the time, y-axis you have the height, and you have the layer coming down in the foremoon and then going up. Just like the solar energy is coming, solar energy into solar angle depends. But you have a lot of fine structure. Where from those are coming? Are they coherent signal, or they are coming from the incoherent signal or some kind of plasma waves? Could be lower hybrid or upper hybrid waves. But even if it is lower hybrid or upper hybrid wave, what is the source of those waves? So I think it is all people are debating about this, and they are talking about the photoelectrons which are present in that hydrogen. They are the source of free energy. So there are a lot of actually plasma physics work that we done with this. So I am skipping. So although we do not know what causes these irregularities, but you can use them as a very good, very helpful diagnostics for measuring the electric field of the ionosphere. And this is actually 50 megahertz per hour. And for the Indian context, I think this kind of measurements are missing. Whatever little is there from the Garanti, and I think Calcutta participates that will give This is the thing which I was talking about. It is now in 2022. Actually, then this particular result gave the linkage between the bubble and the plumes. Okay? It was not done before. So we have to understand that even in this domain, the ionospheric research is dead or ionospheric research got saturated. I think this is something that has changed. So I think that there are a lot of opportunities, a lot of challenges. So a lot of things can be done because this is all like a scanning capability of the radar. When the Calcutta radar is capable with this, they can also do in the scanning in space. They will be able to see from where they are generated and how they are dissipated within the radar area. I will not get into this. So there are a lot of challenges. The most important challenge for application, I think this will be recognized. Can we predict the equatorial plasma model because they call circulation? And how do you link it with the GPS circulation, the airway circulation which is used for navigation? Then coming to the GPS, totally, people thought it was only for the physics reason. But today, the way the GPS are and we are going to the satellite data and deriving all the products from satellite, I think now the question has been raised whether all these products are true. And then 150 kilometer echoes and irregularities continue to be a puzzle. I think the physicists are jumping to explain what they do. The 150 megahertz radar does not detect. So it is only 50, 30 around that frequency. What is the frequency difference? Why? Why you are not seeing that? Now coming to the University of Kolkata. So this is the one in the picture in the morning we saw. 475 antenna, 475 transmitter, 25 receivers. That is the kind of capability that it has. And if you look at the power, its power is almost about 1 megawatt. Okay, 475 multiplied by 2, that is the total power. Kilo. So it is about 1 megawatt, 25 receivers. That means simultaneously you can receive signal by 25 receivers and you can do the kind of processing that you want. So it's a phased array, provides you 360-degree beam agility whenever you want to place the beam, place it. You have the modularity, whichever portion you want to choose for your experiment. You have 25 receivers, you can do multiple receiver experiments to do it for imaging and study atmosphere, ionosphere, meteor, spinning. So what the summary, the power is such that it actually comes under elastic. I get hurt and somebody say it is a estimator. Just to buy a horse and stab it as a donkey, I think that is not acceptable. So the system can be used for studying winds, waves, and answer. You have the clear net turbulence, but you have also turbulence tied to the weather phenomena. And what this turbulence is doing to the weather phenomena, because when you have turbulence, the clouds they can collide with each other, they can become bigger cloud, bigger droplet, and then once they become bigger, it's natural they will fall into the common range. So the turbulence has a role to play in the cloud and precipitation system. So that is something that you can do. You can study E region, F region, plasma relative precipitation, many methods. You can study also, this is very, very important. 150 kilometers because of mostly confined to the equator. Nobody knows what is the equatorial boundary of 150 kilometers because we know they are not observed at mid-latitude, but nobody knows what is the boundary, equatorial boundary. With the 10 degree, 15 degree, something that can do that. So the radar system provides unique capability to study meteors, meteorites. This is another domain of research which can go to the astronomy. Radar interferometric imaging application, I think, would be of interest to many of the students because those who are, seeking jobs. So I think it's a very, very important application. Students can be interested in signal processing unit, higher order spectral analysis. They can do artificial intelligence, machine learning on it. Because radar sees many, many signals which are other than atmospheric signals. You have the flights like there. You have many other. For example, the debris, space debris. You are getting signal from the space debris, from satellites, many, many. So these need to be removed from the atmospheric data if you want to do quality experiment. So this is where the artificial intelligence machine learning will help. I think students would be interested in this. My whole understanding is that the system capability with 1 megawatt and 100 meter diameter antenna, I think is quite capable to be converted or used as a moderate infrared scatter radar. Because this is the place where you have the electron availability, you have the maximum electron density. So it is natural that even the power is less, but the number of electrons being more, you will be able to detect signal. So that's my understanding. So it can be done. You can study moon. You send the signal, you can characterize the moon, the echoes coming from the moon. You can see the space debris. There are a lot of now space awareness is increasing because a lot of debris are coming. So many of the participating students who participate in this, they can use artificial intelligence machine learning in this. Of course, this can also be used 50 megahertz low frequency radio astronomy or some kind of radio burst from various sources. Only thing is that you have to look at it. When you talk about the very fast changing process, you can, because you have the phase delay system, you have multiple transmitter receivers, you can fire the beam not one beam at a time, you can fire actually multiple beams, 3-4 beams that you need. You can get the beam vector very short time, in few seconds, which will provide you an opportunity to study short scale. So this is something that you can do. So of course you have the capability of scanning the beam in 360 direction, so you'll be able to do kind of imaging of the system. This is something somebody might be interested because Institute of Radio Physics and Electronics, I think they are not familiar with the word called SIMO and MIMO. This is the single input, multiple output, multiple input, multiple transmitter, multiple receiver, single transmitter, multiple receiver. I think this is a concept which is there in the cell phone technology. I think this could be used and this could give some new information about the atmosphere. And of course, we have formed a kind of a virtual network of such radars. You have the radars, Nainital, Guwahati, here the Meghnad, here Gadangi and Cochin. Actually, this particular facility, this particular radar, not only can do something overhead, but also contribute to a large scale system that we are covering or studying through the network of radars. So it can go to the application people. I think with that, thanks.
And we understand that such a huge topic cannot be completed within time stipulated for you. Once again, we thank you. And if there is any brief one questions, I can just take.
Mention that rack scaling concept would be applied to what I see mentioned on the different layers of the rack scaling
Here you see the layers and uses. The layers, the section layers and uses. Can you do the same for the atmospheric layers?
How that can be achieved. So I think I tell you the thing is, you have the different index fluctuation which is random. We do not know everything. But if you take the Fourier transform, or you do the filter of the different index field, then you will see the different index mu is very random from some of space. Okay? And that particular lambda by 2, if you do the filtering, then you will see some kind of thing. So this is the equation. Rest of the things which are following in between because of randomness, they are also reflecting, but they will not contribute because the place that with which they count, they are not coherent. So that's how it is it's a mathematical basically convenience. So you can use it. So the other phases will not contribute. So what you will get is only from the equal space. Those will be the phases left. The vision will be different, but as long as the ranges are same, yeah. So it's like A1, A2, A3, AM. So keep on adding samples. That is what is contributing to you. Rest of the thing, although they are coming in the full rate.
Thank you. We cannot take any further questions because of the paucity of time. And I request now Professor Anish to offer a minute to Dr. Now, I will take 2 minutes break and will request our HOD to inaugurate the departmental report.
So because our Honorable Registrar, University of Calcutta is present, so once this program was conceptualized, we realized that in the absence of any CAS report, so to say, which we used to prepare every year, meticulously earlier, or the UGC NRC, it is high time that we should showcase the achievements of the department at least over the last 5 years. Because the last consolidated departmental report was prepared way back in 2016. So many of our departmental colleagues, they took this arduous task of compiling the inputs from all the 22 faculties that we have now. And it is indeed my pleasure to hand over one of the first copies of this departmental report to our Honorable Registrar. We will also send officially copies of this to other university authorities as well as to other institutions and funding agencies, because it is the funding agency which needs these inputs from the department more than we internally. So, sir. That is also coming up, the NAC accreditation and the visit.
Thank you, sir. So it is my great pleasure to invite our next speaker, Professor Auditorium, former director, SN Bosch National Center for Basic Sciences. But before that, I would like to ask Professor to felicitate Professor Chaudhary with a bouquet of flowers. Now I introduce speaker before you, Professor Chaudhary obtained his MSc from IIT Kanpur and PhD from All University, Dhaka, USA, He had postdoctoral experience at the Max Planck Institute, Stuttgart, and Alexander von Humboldt Fellow. He worked as a professor at Indian Institute of Science, Bangalore, and as director, and National Physical Laboratory, and New Delhi as a director, and also director of Western Coast National Center for Basic Sciences, Kolkata. After his superannuation in September 2014, he continued there till September 2019 as distinguished professor and J.C. Bose National Fellow. Since then, he is associated with Central Glass and Ceramic Research Institute, Kolkata, and ACRP Distinguished Fellow. He is also an honorary professor of IIT Delhi. His research interests cover a broad areas of problems in condensed matter physics and materials physics. He has more than 300 journal publications and 6 granted patents. He has supervised more than 40 PhD students. So he is a fellow of national academics of all national academies in India and is a winner of S.S. Bhatnagar Award in Physical Sciences in 1994, along with several other awards. He served the board of ACRB, IIT Kanpur, and IISER Pune, UTC, and Department of Academic Innovation. So, with this word, I request Professor Chaudhary to kindly begin his talk.
I think, am I audible at the back? Yeah, then why should I be using that, fantastic thing? Anyway, I am used to teaching big classes, so I can shout as much as you want. So I have no problem with that. Now, I am scared. You know why? I see all the distinguished alumni and people are really scared of me. No one in particular, but someone they are seeing in the audience are really scared. Anyway, jokes apart, I will be very brief. And I know that I have to be brief, for I am also hungry. And I also know that I should not be very technical. And you know what the best thing when you are talking in a distinguished gallery, don't be technical. For we had a biophysics department in IISc. The joke was that they taught physics to biologists and biology to physicists. So never be technical when you have such a distinguished audience. But anyway, when you look into this fantastic journey of this department, actually I have been very fortunate to know some of the distinguished alumni of this institute, personally and professionally. One is Professor A.P. Mitra. He really took me to arms when I moved to MPL, and he just wanted me to play a very important, very sympathetic role in arranging the next RC meeting they did their General Assembly. And also, he was doing the universal experiment at the time. He wanted that the Okay, I think this is got an echo kind of coming down. The signal really decays. Okay, fine, no problem. And I also know very closely Srivanda in Delhi, another very nice gentleman and very learned man. And I know very closely Sujit Mitra, who is my Crystal Dada. So, I feel very proud to see all this distinguished alumni from this institution. Though I am not an alumni of this institution, I knocked at the door of this very institution from very childhood days. I think you know why, it's an interesting story. But of late, I am knocking at this institution through the radar project. For example, I am ranked non-expert in this area, but somehow I still put it into this project, but it was a fantastic experiment. And believe me, first time I knocked at the door of the Auditorium station was when I was barely 4 or 5 years old. Not that I was doing the experiment there. There was a gentleman by the name of Dr. Saha, and he used to be doing experiment there. And Dr. Saha used to have a dark room where he used to convert this negative into positive. And that kind was a fantastic thing for me. And after all the debris that he used to have this role, that one used to give me to play. So that was my first experiment with IIT. But coming to serious things, and I will not repeat what this was also shown by Professor Basu, but this is an iconic statement, and when you look at the 75 years of journey of this particular institution, definitely nothing can beat this particular statement. Now, my talk will be very brief, few introductory remarks, and reminiscent of the pioneering award done by Professor Nag and his close associates. You have questions there, of course, Professor Stein and Professor Basu. So all questions on this matter should be directed to them. And in that, I will take a repeat of 700 electrons as I understand. It's a very big subject. We have to do it in a half an hour talk. And I decided I should do a Ganga Pujo with Ganga Jal that I that through a couple of already said to one couple of slides to show that we are still active in this area. Now, if you look into this, has already shown that it started in 1924. So the reason I bring it up, if you look at Auditorium started in 1936, and the knowledge and the expertise base needed for Akashbali, which is in the awareness propagation, was given by this institute. For what Ashik was saying that whether we were the only institute at that time when we started, you are the only institute at that time. There is no other institute where awareness was taught. And it goes to the greatness of Sir Asutosh that when Professor Shishir Mitra was appointed as the Khaira professor, he helped him to actually start this course on ionospheres and all that. And there is another thing where Shishir Mitra got his inspiration from, and that is from Sir J.C. Bose's radio experiment. And what I'm going to talk on semiconductor electronics today has a golden heritage connected to this particular city. And it's not just an emotional connection. Just look at the one very important data. One of the biggest achievement of modern day solid-state science is photo detector. You have your mobile, this thing, that there's a photo detector. Now just imagine that was detection of electromagnetic wave by a semiconductor. It was done in 1904 by Sir J.C. Bose, and that gave the first patent in solid-state electronics in the whole world. And that is the golden heritage on which this particular city stands and this particular institution got its inspiration from. And we are all proud that what IRP has taken forward is the golden stage that was set by Acharya Vasu, Jagdish Chandra Bose, and his very distinguished students, Professor S.T. Mitra. And this is how his detector at that time looked like. And when you look into the images common around today, you just go to YouTube. Every day you are getting some fake news from these critics quoted from God and all that nonsense. But there are fantastic images that comes out. And if you look into the 30 years, it goes from Hubble to James Telescope. There are of course new technology, new science, and new everything. But what played the most important role at the time was the development of the photo detector and semiconductor photo detector, and we feel proud we started from this city. Now let me quickly come to the contributions of Professor Piarna. It was so huge that it was difficult to, when I was preparing it, I was thankful to Ashik that he gave me the job to do it for I could learn many things. And then I was also very scared to do these things. Okay. Now let us look into the three main areas where Professor Na's contribution can be really categorized. One is definitely early work of the microwave and high frequency processes in semiconductor, then hot electron effects, and more importantly, at the later stage, and the good part of his work was in complex semiconductor infrastructure, particularly growth of better structure, quantum memories, electron scattering. And it is very important to see that even with those facilities which may not be at par with many of the advanced labs in the world, the amazing high quality work that was done by their group. Now, what I do is that this particular contributions, this particular institute play, I try to kind of see whether I can embed into this development of this semiconductor physics and semiconductor industry very quickly and try to understand the implications of their work. Professor Na's first work in this field of semiconductor physics came in, I think, 1962, where I think many part of the Auditorium was not even born. His last paper, both single author, were 2004. And you can see the shift. He was talking of carrier lifetime measurement in microwave, then he was talking of the indium nitride and the semiconductor structure and the quantum waves. So it's a span of 42 years. And in this span of 42 years, it is some of the glorious journey of this particular institute came from this 42 years. Now, if you look at the modern science and semiconductor technology, it really defined human civilization. And you know that in 47 it started with the transistors, shockwave what, then the junction transistor in 50, and of course the IC proof of concept in 1958. Look at the time scale, that is what I'm telling you. It's the late 50s and early 60s when international things happened. And this is precisely at that time also, this particular institute started getting into that area. Of course, this war gave to very important price, but it also opened up, you know the $1 trillion businesses and 60 years that changed the way mankind communicates, but doesn't communicate. But people who are owner of mobile, they don't communicate to the next person. To you, they're talking to the mobile. So we are not really communicating in the communication age. So that is what sometimes technology leaders do. But it has come to one thing. If you look into some of the important areas in semiconductor physics that came up over this last 60 years, and we are really very active these days. One is ultra-sensitive photodetectors. There is no doubt about it that that is one area where a lot of work will come in, particularly if you go to longer wavelength. There are sensors for wide range of applications with cloud capabilities. For the IoT sensors, the biosensors, millimeter wave devices, another thing which this particular city has a role to play, and now the neuromorphic devices. And come to it again, you come to the modern IC and chip making and all that. So this is the whole 60 years of journey that has been happened. Now, if I take the whole development, and if you look into it, there is this wafer, modern wafer that people are working nowadays to more than 12 big wafers. And if I take this, all the development that has happened in the last 6 years, particularly in semiconductor science and technology, I can put them into three main pillars. Pillar one is the growth and characterization of high quality semiconductor crystal. And I'm very happy to know that this particular institution has a culture of growing high quality material, and they are continuing that culture. Then tools and techniques for fabrication of semiconductor electrical structures and devices. And the third one is the concomitant development in science and particular solid physics that believe me, and that is what I feel proud, that Professor Knox and his co-workers actually contributed to all the three pillars, and more so in the area of understanding the basics of physics. If I go through the archive of the Indian Academy of Sciences, I found out that he has 191 publications and 3 celebrated books. This particular book I started, or when I started my PhD, the first book I read in semiconductor physics at the level of research was this particular book. I started my PhD in 1975. I felt really proud that it was written from this city by a person belonging to as an Indian. And all these books are extremely well researched, particularly this one is a very well, it's a part of a well celebrated series and only well read books. Now, what I could understand by looking into Professor Nath's work, and I think particularly my colleagues who have actually worked with him can tell me that he really felt very comfortable both in theory and experiment. There are not too many scientists in the country who are comfortable both in theory and experiment. And that is maybe that is what Professor Nath meant straight to us. And he imbued this culture into all these workers and students. So if you look into the types of publications which came from these particular institutions, this coming together of the concepts, the theory and the experiment, I think that still remains the mainstay of this particular institute, and it should be strengthened. And that is why we all should feel very proud. And this is something what I already said, that is what we have worked on. And there are some celebrated work, particularly two-dimensional electron gas, which really was pioneered in this country to work on, particularly the theory of electron scattering and such what. And I could see Professor Basu and Professor Susan can get associated with that. Now let me just try to see where this works stood vis-a-vis other works going on in the country. And what I'm telling you is slightly authentic information, what I authenticated by the horses. Now, let me tell you that it's since 69, it's a major work where the solid-state physics group or solid-state electronic devices group of these institutes started working. And even he started working on mercury cadmium telluride, which very few will. He started working on mercury cadmium telluride long back. Theoretical work he started, but very few people knew about mercury cadmium telluride in those days. And it is such an item, if you mention it, FBI, CIA will come to your lab. I tell you a true story. Don't mind me taking 1 minute to tell stories, which I put before lunch. See, I had a good friend in ISC Bangalore, his name is Rajesh. He decided in 90s that he would start working on mercury cadmium telluride. He started collaborating with a Indian-born friend in US, somewhere in Chicago. Within 3 weeks, we saw some suited, booted Americans walking into his lab. He called me, "Hello, quickly, आ जाओ भाई, क्या है this? कुछ problem में फंस गया." क्या है? This is from American consulate, which is FBI, CIA, commercial, and etc. etc. They wanted to know how bad a guy is that you wanted to work on market and telluride, and that too some American colleague, thanks to the great democracies and great professors of science. And Professor Nah's leadership, particularly in the infrastructure work, is what noting. I talked to Vikram Kumar, my colleague in ISC Bangalore, who headed SSPL, and he really started the NPL work on PMRC Meghnad. TIFR had checked it with Bridge Aurora. He had a very nice YouTube lecture. 25 years last year. Then GN was moved me back to Kharagpur, cannot talk to him now. If I see that this is you started experimental work in infrastructure was almost at par with possible 4 other leading centers. And that is where the thing goes. But what I find and what makes me happy, theoretical and modeling work in infrastructure, this institute was needed. So if I want to look into the various developments that has happened in the country, it's very important area, the important contribution of this particular institution should be recognized, and I think it's not recognized well. And this 75 years, we should be working to see that it is recognized well. Okay, just one technical slide. See, the early work from the department in the infrastructure was mostly low barrier semiconductor. I'm happy to see that in the gallium nitride, there was very high quality work of making gallium nitride has started, has been done in this institution, thanks to our younger colleagues. And I can only tell you one thing. I am trying to, really associate with gallium, not so much as versus to the gallium nitride work in the country. But the gallium nitride work, which is crystals of the hairs which are grown in the Salt Lake campus, my next door neighbors, and the best in the country. And this time certified with a lot of pride that it is true. And this slide is okay, but what are the device physics than today? And that is two things are important in the device physics today. One is miniaturization, other is diversification. First one, as Indians, we can only read and learn, but moral is out of reach from us. But diversification is one area where you have essentially heterogeneous integration, analog integration, applications in digital platform, and particularly putting new features on this digital platform in the network itself. Let me take borrow this slide from the semiconductor industry roadmap, and you can see there are two verticals. One axis is on the more and more shorter and shorter features, what you call move, law, etc., etc. And the other is diversification. And the word for it is that it is essentially digital system on chip SSC, and it is digital content system in packages. Here a lot of analog things are getting integrated into the digital platform. If you ask me that what is the area you may investigate or kind of pay our money, this is where I think. And you can see the heterogeneous technology, they got almost everything that where you can pay, and that is where the semiconductor becomes important. Now, if you look into it, it started with 71 10 micron technology. Then this is something that really revolutionized the computer field. The CPU or Intel 8080, and this is where the I7 fixes stacking today, and you can see the wafer size that says 200 nanometers. Well, the Indian capability today, if you look into the Indian capability of semiconductor lab in Mohali, they can handle 18 wafer, and the diameter width is 0.18 micron. So there is a big gap that you may have to kind of do it in the Indian scale. And what is the thing going in the lithography? This is the most important lithography thing you can see that is extreme UV lithography done at 30.5 nanometer, and it is based on plasma, metal plasma source. And when you go to this wavelength, refractive in optics doesn't work. These are all reflective optics, and this is a complete high level of development that come in the last few years. There's one company in Netherlands which is making it, and it is becoming a lot of political things when one company makes it. And in 2019, they really started getting into in a big way. This shift the first system into 2022 to quite a few R&D labs, and by next year they are going into commercial venture, and the latest model costs $300 million for you. So you can see that where the cost is going. Well, in diversification, and there are a lot of things that has come in, particularly integration of platform. And I just listed here where these particles will lead to this kind of diversification. Definitely, it is compatible to CMOS platform, high frequency compatibility, thin transistor with planar devices, new gate structure, and unconventional dielectric, and 3D integration packaging. And if you look into it, what are the things which are coming over here? Low frequency analog to digital mixed signal system, MEMS of various kinds, and definitely pop electronics and things like that. Just to show you how does it 3D integrated integration look like today. You have the sensor that many of us who are sitting on this platform over here, and mainly they are 3-5 type. This is analog to RF system again 3-5 type, and then it is getting integrated to the digital logic and to the signals. And you need a quality fab refer to maybe I made or some of the manufacturers to get into this kind of integration. And this is what we are moving from. See, if you look into these sensors that you have this kind of external integrated, vertically integrated sensors which is signal processor. Okay, just now I have another 5 minutes where I can really create my own now by throwing in some of the just one or two slides that we will see. And now our theme is essentially engineering nanomaterials of 5 different materials in the platform using FID and electron lithography. And the area that we really ventured in the single nanowire electronic photodetectors. Photodetectors made from silicon nanowire oxides. Gas sensor made from perovskite, like particularly for flexible electronics. Now, what we could establish, actually, in 2009, we established our first electron facility with optical lithography. And we were able to really go near 100 nanometer, 50 nanometer kind of lighting with FIP is smaller. And we are supported by the transmission. What I wanted to show that all this work was actually done in the city next door to our capital university setup. And this is the thing that we have used, that is the Helios 600, which is the electron beam, ion beam, and other things associated with it. And this is a similar system, I understand, the nanosector in Calcutta also has. And we use, it is a 50 piece small class of the group, and it's a very modest setup, but we could do some work. Now let me tell you that how we do integration. So generally integrate a single nanowire with contact pads by using some kind of a technique, and you can see that this is a lines 500 nanometer lines is connecting a 5 micron silicon nanowire, and what it gets me, this is a 5V connected nanowire 45 nanometer, and here we could go to just about 100 nanometer or slightly below. Now one of the main achievement that we could do is to make photodetectors from single nanowire, which could go up to 10 to the power 7 ampere per watt. For silver it was 10 to the power 4, for the aluminum it was 10 to the power 7. You can see that these are the electrodes, this is the nanowire, and they are anchored by platinum anchor. So that is where our fabrication is. And we can now detect down to 0.1 picowatt, which is the noise sensitivity. Okay? Now let us just quickly touch on physics. What is this enabling physics which gives us such a high detective responsibility when you know that commercial detectors are 4 to 7 orders less than what you can get? When you see that, if you look at the junction, the electrons are all separated by the axial plane. But what we found out that in a nanowire, due to the oxides and etc., there is a radial field that separates electrons and the holes and enhances the time, and you can get such a high responsibility. Now, a very quick work which has been done with my colleague was to get into hybrid structures of the organic, inorganic perovskite halides. This is a darting of people who work on solar cell research, but we thought that to go do something else. We built actually a gas detector, and this is, you can see that it is for actual use, and it is going into technology transfer through DC. That you make this material into a spool, and it's yellow color, sorry, when it's spool black in color, get exposed to ammonia, it becomes zero. It's very important for people who are working in cold storage and such systems and mid storage. Like Lucius is very interested in getting this kind of sensor, for they have storages where they have stored their meat. Okay? And I skip it and just to keep it tight, and I pay my tribute to the great scientists and academicians who made this institution what it is today, and we wish another 75 years of work. After 75 years, I'm pretty sure, if not all, but most in the auditorium will not be here. But this institute will be here, and this institute will shine. Thank you.
Thank you, Professor Rajendra, for nice illuminating lecture covering a large scanning range. And we feel very honored, sir. And I can, because we are running out of time, I can just take one question if somebody wants to ask. Okay, so people are hungry, it seems. So I request Professor T.P. Saha, sir, to offer a memento to Professor Rajendra. Thank you, sir. No.
Just one moment to interrupt. We are very fortunate that Mrs. Chakravarti, wife of our revered teacher Nirmal Mohan Chakravarti, and his daughter Mitali Chakravarti are present here. And on behalf of this institute, it's my privilege to
Thank you, sir, and thank you, Mr. I feel proud to name our next speaker, Professor Bhattacharya, former Professor of Indian Statistical Institute, Kolkata. So first we felicitate Professor Bhattacharya with the bouquet of flower. Please, hand over. Okay, sir. So let me introduce the speaker before you. Professor Bhattacharya has been on this Studies faculty of Indian Statistical Institute, Kolkata for more than 35 years. After retiring from ISI, he served as distinguished visiting professor at IIT Kharagpur during 2018 to 2022. Currently, he is engaged as visiting professor of computer science and engineering at Auditorium, Odisha. He received the basic degree in physics, BTech and MTech degrees in radio physics and electronics, and PhD degree in computer science, all from the University of Calcutta. His research areas include VLSI testing and electronic design automation for integrated circuits and microfluidic biochips. He has published more than 400 technical articles and he holds 10 US patents. Dr. Bhattacharya is a fellow of Indian National Academy of Engineering, a fellow of National Academy of Science, and a fellow of IEEE. So, I request Professor Bhattacharya to deliver his talk.
So first of all, please maintain silence, please. So it's my great honor and privilege to be here today and to speak on this occasion. So radio physics is my alma mater. I spent 10 years here, entered into the campus in 1972, made an exit in 1982. So with my BTech done here, MTech done here, PhD also done here. 10 years of experience. So I was fortunate enough to have been taught by many legendary teachers like Professor Jay Kaur, Professor Chaudhary, Professor B.R. Nag, Professor Pankaj Prabhu, Dr. and so on. And it is my pleasant duty today that in this talk I am going to pay my humble tribute to the works of Professor Arun Kumar Chaudhary, who made a significant contribution, particularly in the area of social theory and its impact on modern computing. So, as you see, my title is an inspiring story of footprints on science. So, it has a dual meaning. In one hand, this is the story of extraordinary vision and unfathomable legacy that he left. And on the second hand, and on the other hand, this is a story that how his work impacted the modern VLSI technology or the technology of integrated circuit design. And as you know that integrated chips are built on silicon, and silicon is abundantly available in nature from Mother Earth, that is from sand. So he left an indelible mark of footprints on sand, and you have to go through his work and so on, you will see that not only during that, even 50 years ago, what he has done, you will see an enormous impact even in modern times. So today we have many coincidences of the 75-year celebration. First of all, the celebration of the 75 years of the radio physics department, and then 75 years of Azadi Ka Amrit Mahotsav, and at the same time, it is the 75th anniversary of transistors. And we just learned that it is also the 75th anniversary of the Saha Institute of Nuclear Physics, where we are still, and this is the auditorium here, right? So we have so many coincidences. So the Institute of Radio Physics and Electronics, as you see that it's 21st April 1949 was the date of establishment. So it was founded by Professor S. K. Mitra and one of the craters on the moon that has been named by after Shishir Kumar Mitra on the far side of the moon, and it is known as Mitra crater. And also the celebrated research monograph on our atmosphere. And in fact, when we were students, our atmospheric course was based on this textbook. Okay, so let me focus on the contributions of Professor Arun Chaudhary. So he joined RP in 1949. As you see that he was the founding faculty member of this department. And so he pioneered research in computer engineering in India. He started with control engineering and circuit theory, circuits and system, and then switched on to other areas. And he built another computer at RPE. So possibly it was the first another computer in India, but the documentary evidence in support of that, it's still yet to be retrieved. But his most important contribution is in the area of Boolean logic and logic in minimization of Boolean functions and logic synthesis. So he worked in the early days of Boolean logic synthesis, and interestingly, he initiated VLSI research around 45 years ago. And that's quite amazing. And he got them also graph theory and optimization and applied those concepts in synthesizing logic and in solving many other optimization problems. And he mentored more than 60 PhD theses. And recently, just a few months ago, in January of this year, we celebrated the celebration of Professor Chaudhary in Calcutta University at the Department of Radio, at the Department of Computer Science and the School of IT. And as you know, that he also founded the Department of Computer Science and the part of this area. So, since the canvas of this work is too wide, I will try to focus on only on his contributions on Boolean logic synthesis and various design. And in my opinion, this is the area where his work has exerted the most profound impact. So, minimization of Boolean switching functions, logic design, and in the area of logic design, he worked in the area of what is called the cellular realizability, then synthesis of sequential circuits, synthesis of threshold logic, synthesis based on Ritz-Muller expression of algebraic normal form, testing and fault tolerance, and real-size circuit design. So this is the scope of the work, and when you talk about that, you might wonder that what are the impacts of this work and in the context of the modern computing science. For example, minimization of switching functions, the work that he initiated, it provides the basis of modern IC design or IC chips. Cellular realizability, the work on cellular realizability, particularly on microcascades. So it has initiated the concept of what is known as today's cellular automata. The synthesis of threshold logic is important in the context of today's neuromorphic computation, which are used for implement artificial intelligence accelerators. And the synthesis based on Ritz-Muller expression or algebraic normal form. It has a very strong connection to what is called the reversible logic, which provides the foundation of the modern quantum computing. And testing and field fault tolerance and VLSI circuit design, those works lead to what is called the electronic design automation tools for integrated circuits. So these are the scope of his work. I will touch upon only some of these, particularly these three topics: logic minimization and synthesis of digital circuit, testing design for testability, and synthesis and testing based on Ritz-Muller canonic about what is known as RMC logic. So first of all, let me start with logic minimization and synthesis of Boolean function. This is the very favorite area of Professor Chaudhary. And in fact, so this is the first paper which he wrote, application of Boolean algebra in the design of switching circuits. It appeared in the IET Journal of Research in 1959. So those who are students of electronics, they are familiar with the Coin-McCloskey method of minimization, right? So that appeared in 1956. Notice that this paper appeared in 1915, only just 3 years beyond that, and he used the concept of Boolean hypercube and the distance between vertices to minimize the Boolean function. In fact, note that. So this work was done. This work was done in the Institute of Mathematical Machines, Czechoslovakia, which Professor Chaudhary visited, and there we met Professor Anthony Soboda, who was one of the four fathers of switching theory. And that was the beginning of the switching theory research in India. Professor Chaudhary was the first person who initiated research on Boolean algebra and logic design. First time in India, sitting in the radio physics department. Remember that during that time, there was no internet, no computer, nothing else. Only a converter and few journals in the library. Just using only those things, nothing was available. So it was amazing that how Professor during that time could contribute so much and so profoundly during the based on the intellectual, based on the intellect, imagination, and innovation. They could make profound contributions in different areas like this. And during the next 30 years, they published more than 65 papers in this particular area. So I'm going to focus on these. These are the papers he wrote in the early days of switching theory, sitting in the radio physics department. And some of them are very famous. This lecture with SFDAS, where the minimization of switching function utilizing the connected power from matrices. So the work with Professor L.S. Basu, mechanized charts for simplification of switching function. Notice the time interval, the time span, 1962. So sitting at that time, he was working. This is the first work, and no one in India could ever thought of that working and this kind of new area. And then it continues. And so let me focus on this one. So for example, how they screen here?
Yeah.
So this is stage of Robert's paper, complementary function approach is a synthesis of NAND networks. You notice that the logic synthesis is still a mystery. Even the most modern design automation tool cannot figure out the optimum design with just full adder bit, just a full adder circuit using only NAND gates. So logic design is always an art. So optimization problem is still a difficult problem. And Professor Chaudhary also worked in the area of sequential machines. So this is an area which nobody understands. The complexity of sequential machines and optimal design is still a challenging problem, even today. And we have seen Professor Chaudhary from a very close quarter. And we see that he could walk through the different labyrinths of sequential machine in a very easy fashion. So his depth of knowledge in the area of Boolean algebra and in financial machine was really amazing. So why logic minimization? The work Professor Chaudhary initiated is important. Okay? So this cost minimization is fundamental to digital logic. And this is fundamental to IC chips, processors, and embedded systems which we use today. And the synthesis depends on the synthesis type and the choice of logic primitives. That is whether you are going to design what kind of logic primitives you are going to use. And it impacts the silicon chip layout, wear, knowability. And it leads to automated design, what is called the design automation tools, logic synthesis tools. And as you see so there is an empirical formula that the cost of the IC chip is proportional to the 4th power of the silicon die area. And what is that? That's like the price of our mobile phone or laptop. Everything depends on the size of the silicon chip. The size of the silicon die area, that's why the cost minimization or minimization of logic is a fundamental problem in modern IC chip design. So it's like, as we know that IC chip is something which has, so it was initiated with the birth of transistor in 1947, and it has influenced almost every areas of civilization, starting from control and area, in automobiles, in computing, in communications, in Internet of Things, healthcare, signal and image processing, and so on. And perhaps after fire, wind, and electricity and wireless, the IC chips and Internet are possibly the most promising wonders of this century. So they are all permeating game changers. So in this context, I just like to recall what Archimedes said when he discovered lever. So this is the marvel of mechanical advantage. So Archimedes said, "Give me one firm spot outside the Earth, and using my lever, I could move this planet." Now, likewise, what is the marvel of IC chips? So just give me a spot in my palm, and I will smartly command the planet Earth. So technology scaling, Moore's law. So Professor Rajshri also talked about this Moore's scaling. So what is Moore's scaling? See, in 1961, the first IC came into existence. There was the first IC which was fabricated. It comprises only 2 flip-flops and 4 transistors. So that was 1961. This is the first microprocessor which Intel marketed by Intel in 1974, and it contains around 2,100 transistors, just like the seating capacity of an auditorium. Now in 2021, this is the AMD Ryzen processor. Well, it comprises 4 billion transistors on a single piece of silicon. This population of Asia. So this is what is called Moore's law. Gordon Moore, the co-founder of Intel Corporation, just passed away last month. So before the discovery of, the first microprocessor came in 1970, and this is the scenario from 1961, 1969, just 1 year before that. So there was the Apollo mission. So in the Apollo mission, what happened? So they used this Apollo guidance computer, and it comprises 3,000 knowledge using RTL logic. Okay, so you see this why logic minimization or this logic circuit has made a profound impact in different areas. Now, what is happening today? So this is in 2022. So this is NVIDIA graphics processor unit. You know what is the number of it has been built using the Taiwan TSMC 4 nanometer technology, and it has 80 billion transistors. So 80 billion transistors, this is 10 times more than world population. So many transistors on a single piece of silicon. So this is Apple 3 nanometer technology. It's coming up for iPhone 15 phone, and it has 20 billion transistors. So you see this now. Recently, you must have heard the news of global chip shortage in 2020, and that has impacted the automobile industry and causing a loss of the US dollar around 200 billion in revenue. And you see that India Semiconductor Mission that was initiated by the government of India in 2022, and the government has been given a funding of 76,000 crores to initiate and to encourage the establishment of fab in semiconductor areas like display semiconductors, silicon photonics, sensors, banks, and packaging, and design incentive and so on. And very recently, the Department of Education, Government of India, they have published a guideline on India semiconductor roadmap. So what they are saying that so in few years there will be business with revenue of the order of 60 billion US dollars, and 85,000 engineers will be needed in this particular area. So as you see that this logic minimization, the work on logic minimization or switching theory that was initiated by Professor Chaudhary in this department has led to many EDA tools or electronic design automation tools such as Espresso and other modern commercial tools. So this is one aspect. Now let me focus on the second one, VLSI testing and design for testability. This is another area which was initiated by Professor Chaudhary here, and some of the interesting works were here. As you can see that he also worked on fault tolerant sequential machines, which appeared in untempered transactions in computers. And remember that sitting in the radio physics department, so the professor during that was publishing top-notch journals, the top-tier journals like untempered transaction. That is amazing.
No internet.
No internet. So why testing of IC chips is important? Why this work is important? Now today's IC chips comprises billions of transistors, all sitting at gigahertz and several gigahertz. So faults are inevitable. And so therefore, as you see that, so this is the failure rate what the bathtub so this is the infant mortality, then active period, and then aging of transistors and so on. And the failure rate, behavior of the failure rate follows this bathtub curve. So to ascertain the logical correctness and timing behavior of the circuit under test, what is needed? So you need some kind of checking, design error checking, manufacturing tests to check whether specific types of, to eliminate whether any defects have occurred during fabrication of the chip. And of course, in the board level, system level test, those kind of tests are needed. Field tests, day-to-day testing of chips of systems. And so the first could be any of many tests, like lines stuck at 0 and 1. So typically a signal line is supposed to carry, in case of digital circuit, it's supposed to carry either 0 or 1. Now because the fault, what might happen, it might stuck at 0, so that whenever 1 comes, it will still be 0 and so on. So those kinds of fault might occur. Transistor might get opens or shorts, interconnect might get opens or short, or there may be timing faults. So faults are important. So as you see that today's chips they encapsulate billions of transistors, and there could be design bugs, manufacturing defects, field and defects, the field malfunctioning, and also defects due to aging. So unless you take care of this test phenomenon, the outcome will be system failure and catastrophic event. So just I'll give a simple example. So this is the one human architecture. Everyone who is a student of electrical engineering, he knows this. So we have registers, processors in one side, and we have memory on the other side. So what is happening? So the processor is executing instructions one after another. So the instructions and data are residing in the memory. Okay, so what happens? So the processor, what is PC is the program counter. So what is the content of the program counter? It's typically a 32-bit register that contains the address of the next instruction to be executed. in a machine. So when you execute a program, the programs are loaded in memory, programs and data are loaded in memory, and the computer run and the computer starts. So it starts sending. So the program counter sends the address of the next instruction. It fetches that from the memory and keeps on executing. Now imagine that you have just a fault, just a 1 bit flip error in the program counter. So what happens? Then the address, the address changes because instead of going to a particular position, so it goes to a different location. So it could be a garbage. It may be a different instruction. It could be a data or something else. So the effect will be catastrophic. Right? Just one flip of even 1 bit flip error in the program counter content would be a catastrophic failure. And that is so that is, for example, the complete collapse of the banking system. Just 1 bit of error. So therefore, what is the conclusion? Test is indispensable. So perhaps you have heard of what is the infamous Intel Pentium bug. So this is an example of design error. So it was discovered that there is a floating point. There is a bug in the floating point hardware, and Intel has to recall 4 to 5 million in the Pentium chips, which causes a loss of $300 million during that time. Okay, so what is dependable system of fault tolerance? Okay, so they are very important in life-critical applications like space missions, aircraft, biomedical chips, defense, nuclear industry, telecommunication, automotive, industrial control systems, production line, banking, reservation, and so on. E-commerce. So what is fault detection in digital system? Okay, look at this microprocessor. It has 134,000 transistors. And there is a fault. So notice that a chip is just a black box. Only the input is absorbed, is controllable, and the output is absorbed. So you cannot see what is happening inside. So how do I know that the processor is functioning correctly? So when I was a PhD student, Professor Chaudhary, this is the first problem he proposed to me. So given a chip, look at this chip. So how do you know the processor is functioning correctly? Only the inputs are controllable and the outputs are absorbable. So you need to do only input-output experiment to figure out whether the system is operating correctly, right? So this is a very challenging problem. So let me focus on what is called the timing and delay faults. What is the timing and delay faults? They mean computer hardware. You have combination of logic circuits and some memory elements. So in today's circuit comprises billions of gates like this and similarly millions of flip-flops. Okay, so you have combination logic, cloud, and some flip-flops. So look at in the flip-flop, and these flip-flops are synchronized with the clock. So there may be multiple signal paths reaching a flip-flop, and some of the paths may be slower, or some of the paths may be faster. That depends on through how many gates the signal is passing through. Now, the clock signal should be such that the frequency of the clock signal should be such that it should accommodate the slowest path or the critical path, right? So the system clock frequency is determined by the delay of the slowest path or the critical path. Now, suppose because of the fault of manufacturing defect or field defect, some transistors have become defective. Maybe there is open up or shortage. As a result, the delay might increase. So delay is increased, and the delay is affecting some signal paths, and the faster path now become a very slower path. Okay, so therefore, what is going to happen? So as a result, this delay defect may cause the arrival of the wrong signal logic value at the input, because the clock is constantly faster than the signal arrival rate. So therefore, it latches an incorrect value. So thereby, the entire system collapses. As I said, so this is an example that say, you look at this Boeing 787, aircraft. So this is the current return network. What is current return network? In an aircraft, the body is the previous aircraft like Boeing 787. The body is literally conducting it, and there are so many sensors were scattered around it, and there is a return current path. So the total number of paths here is of the order of 10 to the power 12. So if some of the paths are getting delayed because of some delay faults, what is going to happen? Well, this US Airways jet crash landed in the Carson River in January 16, 2019. So this is Airbus, another example, Airbus A350, Qantas flight 72, 7th October 2008. Flight nearly ended in a crash when onboard computers experienced several unexpected malfunctions. You know what happened? A lot of physics is involved here, due to cosmic particles. So in the venom, if the charged particles arrive, they arrive on from three main sources: Allen belts, cosmic rays, and solar flares. So when these particles arrive, so you have a logic circuit, for example. So those particles arrive, and in the logic circuit, signals are going zeros and ones and zero. So when the particles arrive, so it might create a one signal. Okay, so this basically it may reset some flip-flops surrounding. As a result, so when the particle strikes, obviously there will be the memory cells or registers, they will malfunction, and there will be system malfunction. So faults are important. So when I was a student and searching for a problem, so ADC told us, okay, do fault testing, right? So one day I entered in his room, so it's an interesting story. So as before, so as usual, so two legs are raised on the table, and he was reading Savanya Sutta or something like that. This is your problem. So this is the solution of your problem. Yes. So this is a kid's puzzle, and this is the solution of your problem. Spot 12 difference in 35 seconds. So give two pictures, find the difference. What is it? Well, so there is a flower here, it's not there. Okay. So this deer is raising hand, there is nothing there. So there is something which is not in the first picture but present in the second picture. And there are something which are present in the second picture, not in the first picture. Fault testing is the same. It is the presence of some unwanted action or the absence of some desired action. So fault testing is nothing but, so one description may be the description of the fault free of the nominal systems. The other description may be the description of the faulty or the defective system. So by testing you take the exclusive OR or the set difference between these two. And so given the fault, how difficult it is to find the set? This is the fundamental question in theoretical computer science. And this is an intractable problem known as NP hardness. And so how to find a complete test set? This is a cover problem which is also NP hard. And so today we have many automatic test pattern generator tools. They solve this kind of problem using different kinds of meta heuristics and AI-based tools. So this is nothing but a Boolean equivalence problem. So testing problem is important. That's why I want to give you this message. And as you know, what is the more important topic in computing today? Artificial intelligence, machine learning, and data science, right? But in order to execute this algorithm, AI algorithms or machine learning algorithms or data science algorithms, you need a good or reliable machines, right? If you don't have any machine, how to run this kind of algorithms, right? So in order to have a good machine, what you need? You need a robust system. That's why the logic design for IC chips and dependable systems are very, very important, even in today's context. And finally, I would like to conclude with the third topic, synthesis and testing of regular canonical logic, and show that it has a very close connection to the modern day quantum computing. Okay, so in 1960, as you see that the logic design started. In 1970, the first microprocessor. In 2022, Google announced this arrival of quantum computing. In today's newspaper, we have seen that government of India also sanctioned 6,000 crores for initiate this quantum jump, to encourage research in the area of quantum computing. So what is index to the RMC form of canonical form or RMC form? Professor Choudhury and the students, they worked in this area even in 1970. In fact, we also did some work there. So what is an exclusive OR logic? So I will just demonstrate using some few slides that this AND exclusive OR logic leads to what is called the reversible logic, and this reversible logic provides the foundation of what is today's quantum computing. Okay. So what is great about this regular canonical form? In Boolean algebra, we know that NAND operation is functionally complete. That any Boolean function can be synthesized using only NAND gates, right? NOR operation is functionally complete. And also, one AND and exclusive OR is functionally complete. And so this is called regular canonical RMC form or algebraic normal form. And for example, if we have an OR function, say a plus b, I can always write as a plus a exclusive or b exclusive or ab. Similarly, if I have the negation of x or x complement, I can write 1 exclusive for x. So using these three operators, one, and operation and x or operation, I can implement any Boolean function. Now, so why this is important, RMC order. And the one problem is the synthesis problem. That's what Professor Chaudhary initiated work during that time. How to minimize logic with these RMC modules. And so why it is important today? So RMC expression leads to what is called the reversible logic. Okay, and this leads to quantum computers of today. So what is reversibility? In thermodynamics, reversibility is very well known, right? So if I have a gas at high temperature and pressure in one chamber, and gas at low temperature and pressure in other chamber, if we remove this partition, what is going to happen? Well, gas at uniform temperature and pressure. So this is the arrow of time. You cannot revert back to the original system unless energy is expended, right? So natural processes are typically irreversible. The entropy increases, and in order to restore the original state, energy must be spent. Interestingly, in 1982, Charles Bennett showed that information, there is also a concept called information reversibility. And the information eraser causes an increase in information entropy. So what is computational irreversibility? Suppose you are going to add two numbers, 7 and 3. Output is 10, right? And you know that this is an addition operation. Now, given 10, suppose 10 is given, I know that it is addition of two numbers. Can you reconstruct 7 and 3? That's not possible. There are many answers, right? So even though the computation in the forward direction is clear, computation in the reverse, reconstructing the input from the output, that's not possible. That's ambiguous. Okay, so this is irreversible computation, loss of information. However, suppose I modify this computational module a little bit. So I send 7 plus 3 plus 10 and minus, that gives you 4. Now if at 4, 10 and 4 are given and plus and minus and you can reconstruct this, solving a simultaneous equation, right? So this is an example of reversible computation, information preserved. So what is the significance? Significance is, the significance is far-reaching. And also in the logical space, you have the concept of reversibility. So for example, you will not get, if the input is 1, output is 0. If the input is 0, output is 1. So if the output is 1, input is also 1. So it is reversible. However, if you do an AND bit, well, now you have a problem. So 0, 0, 0, 1, 0, 0, 0, 1, 1. So if output is 0, you cannot say what was the input. There are 3 possibilities. So this is irreversible. Okay? So what is the problem with reversibility? Conventional logic gets up. Conventional logic circuits are irreversible. However, when you design the circuit using AND exclusive OR module, then it is possible to design the circuit in a reversible fashion. And this is based on the Tafawli gate. And Japanese scientist Tommaso Tafawli introduced this gate, whose basic modules are just AND exclusive OR and constant logic OR. Essentially, the RMC logic. So this RMC logic provides you the reversible circuit. Now in quantum computing, it was researched by Richard Feynman long ago, and as you see that Google announces quantum chips very recently, and this processor works on subatomic level, and one day these machines could solve computational intractable problem very fast. Okay, so this is this IBM 50 qubit quantum computer, which was announced in 2017, and so there are many other examples. This is the Chinese quantum computer, which was announced in July 2021, Gigons, and it was claimed that this is possibly the world's most powerful computer at this moment. It solves the problem in around an hour. That would take world's most powerful supercomputers 8 years to crack. So it solved this problem in just 1 hour. So this kind of things are based on the reversible circuits or reversible logic. Okay, so one of the fundamental principles of quantum mechanics is that every change must be reversible, except in noise and measurements. That means those referring to deep coherences. And since the evolution of quantum states follow the fundamental properties called unitarity, and all quantum logic gates must be implemented as a unitary operator, and hence they are reversible. So as you see that the work initiated in the area of the regular logic that provides the foundation of the reversible logic and which provides the foundation of modern day quantum logic or quantum computers. Okay, so that's all in the roots and leaves. The candle can ignite thousand flames and is thus never extinguished. So he was a prolific contributor. Professor Choudhury was a prolific contributor. He works in many areas: control engineering, circuits and system, analog computers, switching theory, logic design, testing and fault tolerance, graph theory and optimization, and more importantly, in my opinion, he was a connectionist. So he could see the connectedness in apparently unconnected things, apparently unrelated things. And that's why you could see given any problem, you could see the fundamental thing which is embedded in it. And to pay my homage, so since he was himself a connectionist kind of thing, so this is the scope of it. So I'm a self that dwells in and interconnects every model creature and the beginning, the present, and the end of all.
Thank you, Professor Jerry, for nice illuminating lecture, journey of synthesized circuits and fault tolerant circuits and logics. So, one question may be taken. Time is very short. So, if anyone wants to ask anything, you can ask. Okay. So, now I request Professor Shen to offer a moment to Professor Shen. For the next session, very quickly, I announce one thing that we have arranged an exhibition in the ground floor of the Department of Reduced Electronics. Please visit there. You will leave this after lunch. Okay, after lunch. So now time has come to summarize the milestones of the department, and this will be given combinedly by Professor Shashank Shen and Professor Animesh Moito. But before the lecture, we will felicitate Professor Shen and Moito with a bouquet of flowers. Thank you. So now I request Professor Shen to begin his presentation.
Summarize today's proceedings. Try to give it a try. And to begin with an excellent introduction about our department from Professor Rasul. Showed us the 75 years journey of the institute, talked about our wonderful teachers, did a tribute to the founder, Professor Esquinito, highlighted the pioneering achievements and the impact of the manpower created on the society as a whole, not only in India but worldwide. Mentioned about first lady graduate engineer from the state of Odisha and another lady graduate from our institute, both are from our institute. In addition to these two names, I found another lady researcher. I do not know, I could not find whether she graduated from our institute or not, but definitely did research in this institute. Her name is Mrinmoyi Ghosh. She had several papers, both individually as well as with Professor Esther. Professor Kasu also highlighted the thrust areas of research in the institute, the different centers that have been created at different points of time, the publication records since the 1990s, notable achievements by our alumni, the books published by international publishers from our faculty, the authored by our faculty, the review articles, patents, and international collaborations with many different countries of the. Also highlighted about the services that all institute faculty members and sectors like the society shared some beautiful photographs of the facilities that were created in the institute in early days and acknowledged to gifts and donations from the getting back. There are several other photographs which are on display on the ground floor of our building. I request and invite all of you to come and see them. After that, we had the first technical lecture from Dr. Amit Patro, Director of ADRL. We paid a tribute to Professor Estimate as well and highlighted his contributions to bringing atmospheric studies to India. And there are very good account of how radars can be used for proving atmosphere and ionosphere. And more about it will be discussed by Professor. I'll skip this topic at this point. And Professor Arup Rai Chaudhary primarily paid tribute to Professor B.R. Nath, highlighted the research or the research tool that he had created in the field of semiconductor physics, both in theory and experiment. Highlighted the important areas of research that Professor Nath gave initiative in the institute, and in many cases in India. We then went into the modern trends of semiconductor research, both in our institute as well as in other institutes, particularly where we have been working, and talked about Professor Nath's publication, which he found from the East archive, and she said for the number, I'll try to get a list from you. Some of the highlights are research on compound semiconductors like indium antimonide, gallium arsenide, indium phosphide, mercury cadmium telluride. And particularly the last one we have pointed out as one of the important compounds in those days for infrared detection. And in 1974, Professor Dr. pioneering theoretical work of triple lattices. In 1982, we started the proof of infrastructure by the liquid physics method. Now we have in our university an MT facility as well. We actually carefully avoided the MOCVD. That's because of the assets involved. And also, Professor Vaishnavi pointed out about the gallium nitride work that Anirban Bhattacharya and his students have done in the Center for Research in Nanoscience and Nanotechnology at the university. And you mentioned that they are of international standard. You mentioned about the IRTS roadmap of semiconductor industry going beyond Moore's law. Talked about the facilities at Semiconductor Complex Limited, which is now standing at 180 nanometer node. And also, moving on the diversification groups that lie ahead, mentioned about the importance of amalgamation of analog and digital electronics, and also about 3D integration. He mentioned about his own contributions at the Singapore National Center next to our CU campus at Sortec. His works on nanomaterials with focused ion beam and electron lithography systems. He also mentioned about some of the other facilities which have been parallel to CRNN. Highlighted the importance of nanowares for high sensitivity semiconductor photodetectors, and also talked about the future of organic, inorganic hybrids in form of perovskites. And the last lecture was from Professor Bhattacharya, just by the ISI, now at Auditorium. He essentially paid tribute to Professor A.K. Chaudhary, another legendary figure in the development of research environment in the Institute of Electronics and Electronics. He talked about his versatileness, areas of research, introduction of areas of research in diverse fields of starting from analog computers, control theory, switching circuits, analog circuits, or circuit theory, as well as graph theory and computer architecture. We talked about the importance of minimization that APC pointed out in those times in the early 1960s. In fact, it started, the first paper product showed was in 1959. Talked about the importance as well as the challenges involved in testing of sequential circuits particularly, and also how to go for fault tolerant designs. He had more than 65 papers on Boolean logic in his lifespan. In fact, Professor Chaudhary was the first person in India, as Prabhu pointed out, to introduce research on VLSI design. And his research mainly focused on synthesis styles of particularly sequential circuits and the choice of logic primitives in the optimal design of the sequential circuits. And he highlighted about why testing is important. He had some interesting photographs showing us what could happen if just one bit could go wrong in typical modern day machines, which are like 64 bits wide. And he pointed out the different kinds of delays that can happen, the different kinds of faults that can arise. Some may be permanent, some may be transient, like those introduced by cosmic ray radiation. And finally, he finished with the idea of quantum computing, reversible logic, and its importance to quantum computing, and mentioned about what is lying ahead in this field. So that is about today's proceedings. In addition to what I've been told by our illustrious speakers today, I'll just give you some amount of data that I could share. Some of these has already been told, so just skip through these things. The early history. In 1925, the first study of electronics was initiated in Calcutta University with the initiative of Professor S.K. as a special paper called Wireless in MSc Physics course. And almost around the same time, in the late 20s, early 30s, the wireless laboratory in the physics department was established by Professor. The research in the wireless laboratory rather, was primarily on ionosphere because that was the mainstay. In those days, electronics meant radio communication or trans-world radio communication, and ionosphere played a major role in the propagation of radio waves in those days. And parallelly, we also took up the design and development of different instruments for these ionospheric studies. The significant contributions of Professor Escamillo in the 1930s and 40s was the discovery of E layer, and today Dr. Mathur mentioned that D layer was also forecasted by him. And also the theory of active nitrogen growth in the upper atmosphere. That was in the 1940s. And in 1949, of course, our institute was established by him. If we look into the research activities of the institute from its beginning, 1949 onwards, it was the ionospheric studies, parallelly electron tube circuits, mainly for instrumentation purposes. And in the 50s, Professor Esteve started working on electron tubes, study of the behavior of physics going inside the electron tubes, and subsequently an electron tube fabrication setup was built in the institute. Microwave research was initiated by Professor J.S. Chatterjee, who moved to Yadupur University to found the telecommunication department there, and Professor G.S. Shanal, who moved to IIT Kharagpur. And the first paper I could dig out on microwaves by these two authors was in 1952. The first paper on communication techniques or communication circuits was by Professor A.P. Chakraborty, who also later moved to IIT Kharagpur, on communication techniques in 1954. The first on analog computer was, or rather the research on analog computer was initiated by Professor A.K. Chaudhary, and later on Professor N.V. Chakraborty and Professor B.R. Nag joined him in the person. I'll talk about it a little bit more since Professor Basu has raised the point of controversy about where the first computing machine in India was built. Professor Chaudhary also initiated switching circuit research, Bhargava has already pointed out. Junction transistors and circuits work was initiated by Professor S. Dev and A. Dana in 1958. Control system work, although Professor Chaudhary was the mainstay of control system research in the institute, but the first paper I could find was by N.V. Chakraborty and A.K. Bangladesh. Of course, semiconductor physics research was initiated by Professor Nag in 1963. And finally, again, Professor Chaudhary on computer architecture and graph theory, which essentially started from 1974. And all these things have been talked about by Professor Basu, so I'm not going into the details of these, but I'll just go into that controversial point. About this, Bhargava may take note. The first paper I could dig out is in 1955, and it was received for publication in on August 30, 1955, published in October 1955, and this formed a chapter on Professor Chaudhary's PhD thesis, or DPhil as it was called in those days, titled On the Analog Computer. It was submitted in 1957. that estimate. In fact, I found that this paper formed one chapter of that thesis. The mainstay of the analog computer was this machine, an electronic differential analyzer, which was actually published after the thesis was submitted. In fact, what I found interesting in Professor Chaudhary's thesis is that there is no list of publications by the author.
No paper was published, but it was
Perhaps they were not published before the thesis was submitted. But this 1955 paper was definitely published. I do not know why it did not mention. Okay, so that was the date. 1955, the first component of the analog computer was built and published. 1957, the thesis was submitted, in which I could find this picture of the differential analyzer. So we can say that 57, definitely the analog computer was there, as built in the institute. And note, I'll just talk a little bit about this. You can see two panels. In fact, there are two racks. The upper part of the rack shows the computing circuits, and the lower part was housing the power supply and allied electronics. So I'll just focus on the upper part. See, as you can see on the left rack, both of them you can see. There are 4 plus 4 operational amplifiers. In fact, each of these rack had 8 operational amplifiers in 2 rows of 4 each. There are similarly 4 and 4 here. On the left panel, these amplifiers were, as I could read from the thesis itself, these amplifiers were configured as adders with 2 inputs each, which you could set through this multi-term precision potentiometers. So each of the amplifiers had 2 inputs to this potentiometers. The 8 amplifiers on the right side were configured as indicators. And you can see there's a sort of removable link in the feedback where you could change or set or connect a capacitor of choice to set up the time constant of the indicator. So the differential analyzer had 8 adders and 8 indicators. And amazing things were done, as you will find from several subsequent papers that were published using this machine. Well, today's students of electronics might wonder why such a big cabinet was required to house just 16 indicators, or 16 operational amplifiers, I should say. In fact, these panels are like 8 feet high and each of them are 3 to 3.5 feet wide. As I could remember, because we as students in 1973 had the privilege of working on this machine for a great deal. Let me just give you an idea about the circuit. Incidentally, this was built with vacuum tubes. Transistor circuits were not that prevalent in those days. In fact, the only transistors that were available were germanium junction transistors, and they were not very stable devices, as we know today. So what we had are 3 vacuum tubes to build each operational amplifier. The first one was a twin triode that accounted for the differential input stage. In fact, only the inverting input was available to the user. The non-inverting input was used to set the offset. Then we had the main gain stage using a pentode bar, and finally a triode working as a cathode forward to provide the low impedance output. And as you can see, there is an internal negative feedback to account for the stability of that. Just to give you an idea about how much space this amplifier itself could take up, let alone the power supply, this amplifier required plus and minus 300 volt supply. Each of them required 6 bulbs each. And give a comparison of a vacuum tube of those days, which is a simple active device that were available to work in those days. Vis-a-vis and complete operational amplifier IC of today in a packaged form. The actual integrated circuit chip covers about hardly a millimeter by millimeter in area. So you can imagine how much larger space it could require. So I think that sets the controversy about the analog computer or the debate about where the first computing machine was built in India. Of course, the EC2, which is the ISI Jadavpur University collaboration, was the first digital computer and built using transistor circuits instead of vacuum tubes. There is no controversy about that. But when it comes to computing machines on the whole, this definitely, in my opinion, is the first computing machine built in India. Because ECU came in the mid 60s. So just to conclude with how the research interest in the institute has diversified, primarily from ionospheric research in the first 5 years, as you can see, ionosphere from the publication report, ionosphere papers on ionospheric research occupied more than 75% of the total contribution, and there were some contributions on electron tubes, significant. In analog circuits and mainly communication circuits, primarily by Professor M. D. Chakraborty, and there were some instrument circuits also. And of course, microwaves through the efforts of J.S. Charity and J.S. Sharma. Next 5-year period, the relative share of ionospheric publications reduced, but the total number remained the same because the total number of publications rose from 53 to 74 in this 2 periods. But other areas started gathering pace. As you can see, the circuit activity took a major part. Computers, through the efforts of Professor Chaudhary and his colleagues, took a significant rise. And in fact, it was initiated at the time in 49 to 53, there was no such activity. And the other areas were just cropping up. And there was no research on semiconductor physics in those days. But in the subsequent 5-year period, the major rise was in the area of semiconductor physics, again, primarily due to Professor Saha. And this gives you a set of numbers in total, as you can see, between the first and the second period, the number of papers on ionosphere was just dropped from 40 to 38. But in the next period, it came down significantly. Perhaps because from the 60s, satellite communication was set in, and in the satellite age, the importance of ionospheric radio wave propagation declined, and that caused a decline in the interest in ionospheric research. But as you have seen today from the first lecture, it has again grown in importance, and we have significant rise in the contribution of ionospheric research in these days, or space science research as it is called. So with that, I'll conclude. Thank you.
I'm sorry, you have to stop for 10 minutes more.
সুশান্ত ভালো বলছিল ওটা পুরো বলতে পারবো না।
Okay, I have to very quickly go through some of the milestones. Mainly, I shall concentrate on radio and space science activities at our institute. Uh, okay, I think this is already mentioned by many speakers. Our institute space science activities initiated in the wireless laboratory in 1925 to 49 at the physics department of University of Calcutta by Professor Shishir Kumar Mitra. Please note that just after the discovery of ionosphere by Atherton and Barnett in 1925, Mitra just returned from his visit to France to start his radio research in Calcutta. Of course, already Professor actually mentioned that radio science had its first milestone in India. Acharya J.C. Ghosh pioneering work on microwave and millimeter waves at the turn of the 19th century. And many of you know that Shishir Mitra was Acharya Ghosh's students in the Presidency College during 1908 to 1912. Mitra's group published a series of papers on ionospheric studies in 1930s. I just point out three papers. This is already mentioned by other speakers, particularly Professor Patro. The first important paper is the detection of E-layer. Although ionospheric E-layer was predicted by other scientists like Humiside and Canadian Humiside, but it was not experimentally detected. So, Mitra, Shishir Mitra and Craig Lockheed, they published a paper in Nature in 1933 showing the existence of E-layer. The next important paper was published by Mitra and Sham in Nature again in 1933. This is very important paper. I think it is also mentioned that actually they got regular reflection from 57 kilometers, which is the D region. Previously, although the existence of D region was known, but mainly it was known for absorbing the radio signal. But Mitra's group for the first time, they obtained the reflection from that layer. That is very important because this subsequently led to a partial reflection technique. And the third paper is very important in our perspective, the perspective of atmospheric radar, because Mitra group was the first one which reported reflection of radio signal from low height, from 20 to 30 kilometers. 20 to 30 kilometers. And you know that at that time, in the paper, Professor Mitra mentioned, in the paper in the Nation mentioned that mechanism of reflection is not known, it is intriguing, because at that low height, ionization cannot be sustained. So there must be some other mechanism. And in fact, we took all these layers to a C layer. You can see that. He designated this layer as C layer just to differentiate it from other ionospheric layers E and F. So these are three very important papers which paved the path of many new techniques, particularly atmospheric radars. Okay, these are some of the collaborators of Professor Mitra. In early days, for ionospheric research, Rishikesh Lockheed, Professor Hort, P. Sham, and S.P. Rose. We are the collaborators. Later, of course, others, H.S. Godal, A.P. Mitra, Intidal Gupta, R.B. Bennett, J.K. Shah, and others, they joined his group. And these group greatly helped Professor Mitra in writing different chapters of his famous book, The Upper Atmosphere. Okay, so this is very important. And of course, A.P. Mitra developed a partial reflection technique to study the ionosphere above 55 kilometers, taking a cue from that paper, Nature's paper, which was reported by Mitra and Sham. M.R. Kundu, who is a famous solar radio astronomer, he also had his initial research stint with Professor Mitra. And of course, later when our institute was established by Professor Mitra, many renowned radio scientists came out of that institute, like Jagadish Bhattacharya, Nihar Sendrai. I think Professor Basu mentioned Professor Nihar Sendrai was Director General of IMT and Dharmajit Gupta Sharma was the Director of NGRI. Now, after the establishment of our institute in 1949, plans were immediately afoot to establish a ionosphere field station at Boringhata, 55 kilometers from Calcutta. The field station became operational in 1954, and this automatic ionoson was installed there, operated there, and that participated in worldwide network of ionosphere stations, providing data to world data centers. Okay. Now, apart from ionoson, there are other experimental areas where works were carried out. One of the most important area was satellite beacon measurements, and Dr. Shanti Basu and Professor Ashish Dajgupta, they took the main initiative and leadership in these experiments, and they actually measured Faraday fading and scintillation with satellite transmission at 40 and 41 megahertz for orbiting satellites, and they carried out a study on total electron content and ionospheric irregularities in mid-60s. And these actually filled a very important gap in the global morphology of low latitude ionospheric irregularity features in their region. And also, Boringhata field station was the first station in Asia, Indian subcontinent, to record Faraday fading of 136 megahertz signal from geostationary satellite. And of course, this was carried out during 1977 to 1990 using transmission from other satellites, ETS-2. Another area in which Professor Deepan Gurgai took the leadership, study of lower atmosphere by cross-population technique at using 2.2 megahertz pulse transmitter. And he also studied absorption of 2.2 megahertz signal in the presence of cast type sporadic E. Now, in addition to the experiments or studies being carried out at ionospheric field station, other groups at our institute carried out under the leadership work under the leadership of Professor Onun Sen, and their group mainly focused on ionospheric propagation characteristics and at LF, MF, and HF broadcast bands, and they are mainly interested in unusual radio absorption due to sudden atmospheric disturbances and atmospheric gravity waves. Ekeshen and Visha published a paper in Nature in 1975 on meteoric ionization of radio wave propagation. Now, during 1980 to 2000, major fundings from Department of Electronics and Aeronautical Development Agency of the Defense Ministry supported a number of projects under the leadership of Dr. Sen on propagation of millimeter waves, training program in millimeter wave technology and millimeter wave scattering. All these supports provided major facilities for creating Center for Research and Training in Microwave and Millimeter Wave Technology, about which Professor Bashu mentioned. Professor Meghnad Kumar Dasgupta, he was a very renowned radio astronomer who worked at Jordan Bank at Manchester with Henry Brown and Art Tennyson, and they worked on double structure of radio galaxies, Cygnus A and Cassiniquia A, and their work is now considered as one of the 10 milestone research in the radio astronomy. And this was the double structure they presented, they obtained using their interferometric measurements, and of course, Cygnus A was later imaged with a very large array system. You can see that, and in fact, this discovery has an implication. I understand that in the discovery of very massive black hole in our galaxy, which own Nobel Prize in 2020. Of course, at the Institute, Professor Dasgupta carried out research in the field of atmospherics, solar terrestrial physics, solar microwave and X-ray emissions, and he published 3 papers, which is very significant, in Nature with Deepak Basu during 1964-66, based on the work done at RP. Okay, now of course, 2000 onwards, the research in radio and space science diversified thanks to major fundings from Indian Space Research Organization under estimating the Center for Space Environment, about which Professor Basu already mentioned, in 4 major areas: lower atmospheric chemistry, atmospheric electricity, radios, remote sensing, and space weather, mainly aiming at studying atmospheric phenomena in a comprehensive manner from the lower to upper atmosphere. So this is the first time a comprehensive study was undertaken. And later on, with all these ongoing activities, our institute participated in many national programs, including causes, ALFI, Megatropics, SINGA. This is an international program. In 2009, our institute was chosen as one of the 10 institutes in India for space science promotion scheme, sponsored by ISRO, under which major fundings were provided for the augmentation of research and teaching facility in space science and atmospheric sciences. This is already mentioned by Ashi. Now these are some of the equipments we procured under the funded projects by ISRO. This is K-band receiving satellite revolution system. This is gisdometer. This is radiometer. This is microwave radar. This is multi-wave radio meters. So these are some of the instruments we procured under ISRO's programs. Of course, more recently, as this is already discussed in detail, Professor Basu mentioned and Dr. Bhakta also discussed about this. And our institute was chosen by Science and Engineering Research Board of PST for setting up a national exterior facility, a project on atmospheric studies in geophysically sensitive tropical to subtropical region, which estimator was sanctioned in 2011 with substantial funding, and estimator facility operating at 50 megahertz with 475 young antenna is phase planning configuration has been installed to study lower to middle atmosphere and atmosphere. And this data facility has become operational at our field station since early 2023. So these are some of the milestones I wanted to present. I think I have finished. Thank you.
Thank you, sir. We are actually running out of time, so I think the question and answering session can be done outside also. Now I request Professor Sushant. Sorry. Now I request Professor Bhavani Sinha to offer a moment to Professor Sushant question. Sir. And I will request Professor Malai Kundu to offer a moment to Professor Anish Shumi. We feel very honored, sir. So we are already late. I think there is an arrangement of lunch in the AC canteen just outside the building. Our volunteers will guide you, and I will just wrap up this program with a vote of thanks. And there is, first of all, I must say that there is no words big enough to thank of you all. The whole program was filled with incredible positive energy and spirit. And we are thankful to all the speakers who are kind enough to accept our invitation. And we are thankful to our Vice Chancellor, Honorable Vice Chancellor and Registers for constant inspirations and encouragement. We are thankful to Dr. Amit Ray, the Secretary Science and Technology, to provide us all the logistics for this program. And we are thankful to University GPO engineers and accounts officers for providing us necessary support. Finally, we give a big hand to all the alumni, teaching and non-teaching staff, technical staff to make this program a success. So thank you all, and we have a lunch and enjoy.
Just the beginning. Okay. We have other plans.
আচ্ছা একটা মেয়ে বানাতেই বলছি বই সবাইকে দেওয়া হবে কারণ এটা প্রচার হবে এটাই আমরা চাই তো চিন্ময় আমাকে নিয়ে করেছে অনুরোধ করেছে এখন সুয়ারদা ঠিক আছে সে সুয়ারদার ব্যাপারটা আমরা দেখে নেব এখন লাঞ্চ হবে তারপরে আমি অনুরোধ করবো একতলার এক্সিবিশন হলে আপনি যাবেন তার থেকেও বড় কথা হচ্ছে যেহেতু আজকে আমরা মিলেছি দোতলায় জেন হল অডিটোরিয়ামে কোনো সময় নেই একটা ঘরোয়া আড্ডা হবে কাজে আপনারা থাকবেন এবং আড্ডায় আমরা প্ল্যান করে যাবো সবাইকে অনুরোধ থাকবে